I try to imagine a fellow smarter than myself, and then I try to think, what would he do?
Charge up your axons, ready your receptors, and shift your lobes into upper beta phase. You are listening to Smart Drug Smarts, the podcast dedicated to helping you optimize your brain with the latest breakthroughs in neuroscience, nootropics, and psychopharmacology.
Hello and welcome to Smart Drug Smarts. I am your host, Jesse Lawler, here to bring you episode number 74 in this increasingly long in the tooth podcast dedicated to the improvement of your own brain by any and all means at your disposal. This week we're going to have the second installment in our Know Your Neurotransmitters series. We had the kickoff episode of this series a few episodes ago with GABA. And now we're moving on to dopamine, which I'd say is definitely the best known neurotransmitter, although as we will hear, it's a little bit misunderstood by the general public, but not you once you've listened to this episode. We're going to be talking with one of the world's leading authorities on dopamine, Professor John Salamone from the University of Connecticut, hearing all about dopamine, what it does in your brain, what it doesn't do in your brain, why you should want enough of it, why you should not want too much of it, and the trials and tribulations of all the rodents who worked so hard to teach us these things. If you hang around until the end of the episode, I'm going to tell you about some interesting results from a recent study about modern Americans' willingness to have sex with robots. Yeah, you heard it right, sex with robots. Doesn't really have much to do with smart drugs, but it is sort of a weird futurist thing that I just found quite interesting, and anyway, we'll talk about that. But as usual, let's get the neural ball rolling with This Week in Neuroscience.
Smart Drug Smarts, This Week in Neuroscience.
So despite the fact that you're listening to a podcast right now, I'm going to just take it as a given that you probably know how to read. And if not, I encourage you to stop listening to this and immediately go out and learn to read, because hey, we now have evidence, not that this should necessarily surprise anybody, but that the learning to read process produces structural changes in the brains of students. Researchers in Germany at the German Institute for International Educational Research in Frankfurt have just proven exactly that. This was research headed by Janusz Linkersdorfer, who is looking at the brains of students in their first and second years of elementary school as they're kind of going through that process that everybody goes through as they learn to read, where you start by sounding out the letters in a word like, jar, J-A-R, so J-A-R, and finally connecting those into sounds, recognizing that, hey, the sound I just said is that word that I already know. Oh, that's how that whole thing works. And eventually the little light bulb goes on over the kid's head, and before too much time goes by, typically over that sort of first and second grade transitional learning to read period, kids can stop having to meticulously sound out every darn word that they want to read and start just kind of visually reading in a way much more similar to what adults do. But kind of surprisingly, there hadn't really been much research prior to this study of what exactly is happening within the brain as that process goes on. In this study, they found two major patterns in the data. First, they found that children that have higher volumes of gray matter in their left hemispheric region that had been associated with the perception and production of speech sounds became more reading proficient in the second grade than those with correspondingly lower gray matter volumes. Probably not so much of a surprise. What was a little bit more surprising was that a decrease, not an increase, in gray matter volume as the children transitioned from being reading ready in first grade to being more reading proficient in the second grade was actually positively correlated with reading skill. These decreases in gray matter volume were in regions that were known to be involved with the manipulation of speech sounds. So basically, as the kids became better readers, they weren't having to rely so much on the sound processing parts of their brain each and every time they wanted to read a word. So it's kind of like there was pruning going on as that transition to a more adult-like style of instant word recognition rather than needing to go through each of the phonemes took place. In children of this age group, neurostructural development is mainly dominated by synaptic pruning processes, said Linkersdorfer. Our results might thus indicate the formation of a more mature and finely tuned cortical network for the processing of written language in the left hemisphere. Excited by these results, Linkersdorfer's team is planning to follow children over longer time periods and further examine how the brain dynamically changes over different stages of reading development. And this is pretty cool because unlike something like speech that humans have been doing for a long time and is essentially sort of cooked into our DNA, the ability to process sound waves into ideas and verbalize these noises that are supposed to express ideas. I mean, that's part of our DNA, but reading, on the other hand, is like a cultural learned behavior that's very, very new and doesn't really have a physiological correlate organ for that skill. So pretty amazing that the brain is so plastic to be able to learn skills like these, but also that there's enough commonalities with the way that people learn that researchers do find these predictable changes in brain morphology as the reading process takes place. And I would like to give a super, super big thank you to everybody that obviously listened to me last week when I was saying that there was going to be some sort of drawing for the people that got us up to 100 ratings on iTunes, because I opened it up a couple days ago and there we were at 100. We got 6 of them, I think, in the past week since the past podcast. I think I will probably not read all these at length because I don't want to sound too self-aggrandizing, but big thanks to Ilana3, Freemind Derek, Matt Gatica, Brian Frost, Johnny Bearcat22, and Aphilion, who said respectively, a great podcasts where the journals won't venture, neurological cardio, interesting and applicable, and brilliant. And yeah, that puts us up to an even 100 ratings, which I can only assume makes some sort of algorithm at iTunes very happy. Certainly makes me very happy. And now I'll actually have to figure out what the exciting drawing among those 10 people is for. I will figure that out by next week and we'll have a winner. But in the meantime, know that I'm just extremely appreciative. Oh, another piece of feedback that I got this week, and I'm slowing myself down to say this because somebody mentioned something that my dad always tells me, which is that I talk too fast, and that's probably true. I think I actually normally talk faster on this podcast than I do in real life because I'm typically kind of excited when I'm recording this, which you'd think maybe after 74 episodes that wouldn't be the case, but there's still kind of a little bit of like that good jitters of stage fright whenever I turn on the mic. But despite all that, I totally recognize that I don't want to sacrifice comprehensibility for evidence of my enthusiasm, so I'm going to try to slow myself down. Thanks to the anonymous listener for commenting on that, because while it's sometimes strangely easy to brush off your parents' opinions that, oh, that's just my dad bitching about something, when some anonymous person says it, then all of a sudden it gains a certain authority. So I will scale back the internal metronome just a bit. And in a throwback to a past episode, I'd like to give a little congratulations to Professor David Nutt, Smart Drug Smarts alumnus, who in a recent crowdfunding campaign got more than double the amount he was looking for to study the effects of LSD, lysergic acid diethylamide, on the human brain. This was something that they had to crowdfund because they couldn't get government funding for the study that they really wanted to do. They raised about $80,000, so it's kind of one of those experiments you go into it with some sort of interesting result guaranteed. Because although they might not know exactly what the results are, what exactly LSD is doing in the brain, it's very clearly doing something. So congratulations once again, Professor Nutt.
Smart Drug Smarts.
So today's guest is Professor John Salamone of the University of Connecticut. He is a Board of Trustees Distinguished Professor and the head of the Behavioral Neuroscience Division of the Department of Psychology there. His research interests include psychopharmacology, neurochemistry and behavior, and apropos to this discussion, the behavioral functions of dopamine and acetylcholine. It's always interesting when you're talking with different academics because some of them are very quiet and bookish and don't necessarily feel that comfortable being recorded and things like that. And you have to ask some questions and pry some information to kind of get things rolling. And then there's others who are very, very social and gregarious and probably used to speaking with lecture halls full of students. I think it's probably safe to say that Professor Salamone is the second type of those. I pretty much said we're recording and what followed was just like a fountain of information about dopamine. So you're not going to hear that much from me in the coming interview. I think he pretty much got to everything that was on my to ask about list without me ever having to give a prompt or a nudge or anything like that. He was definitely the man to talk with about dopamine. So with no further ado, Professor John Salamone. Let's talk about some of the common misconceptions about what dopamine is, what it does. Most people still are thinking of it as the chemical that your brain gives as a reward when you do something correct.
The pleasure hormone or the pleasure molecule is what people call it. Somehow that idea got into the popular press. I mean, there are some scientists who have kind of promoted that. Most scientists who really study dopamine in detail either never thought that or always knew it was somewhat oversimplified or have come to realize that it's oversimplified. The summary statement that you sometimes hear people say is, this drug is released when you experience pleasure. In some cases that's true, but that's only part of the story. It's released under other motivational conditions. So I think if you step back from it, essentially responsiveness to rewarding stimuli is only one class of conditions that dopamine activity is associated with. It's associated with other things too. There's a distinction between liking and wanting. And dopamine doesn't mediate liking, but it does mediate wanting. In other words, for example, the behavioral pursuit of motivational stimuli, things like that.
You're actually willing to do something to get what you like.
Exactly. Drug companies came up with a drug. It's called a dopamine D1 antagonist, icopapam. And in the early 2000s, it was investigated to try to see if it could block the pleasure from stimulant drugs. And so a couple of papers were published in a journal called Psychopharmacology. They gave it to humans, and I believe it was cocaine, the pleasurable effect, the self-reported high or euphoria produced from that drug is not blocked by this dopamine antagonist. There were 2 publications in that regard in the same year. There was a paper very recently from a Canadian group. Marco Layton is the head of this Canadian group, and they were looking at cigarette smoking. They had people responding for puffs on a cigarette as a reward, and they also took other various behavioral measures. And then what they were able to do, they did a nutritional manipulation to try to blunt dopamine synthesis. Basically, the nutritional manipulation is if you give people a diet that doesn't contain the amino acids necessary to make dopamine, then you deplete dopamine in the brain. And for example, the self-reported pleasure or high from cigarette smoking wasn't affected at all. The self-reported craving from cigarette smoking wasn't affected at all. But what was affected is working for cigarettes. So they had people responding on a progressive ratio schedule where they have to press more and more and more in order to get their puffs of cigarettes. That was impaired. So that fits, again, a nice story of if you manipulate dopamine systems, the main thing you see is not so much an effect on hedonic reactivity or self-reported pleasure, but rather in things like pursuit of the motivational stimulus. The more work you have to do, the more sensitive you are to interference with dopamine transmission. And then what we do, we also developed tests of what is sometimes called effort-related choice behavior or effort-related decision-making. So in that case, what you have is a situation in which you're given a choice. You could have a high effort activity that leads to a larger or more preferred reward, or the other option is a lower effort activity that leads to a smaller or less preferred reward. So we develop these tasks, and what we see again and again is that if you interfere with dopamine transmission, particularly in this brain area that was historically linked to pleasure, which is the nucleus accumbens, what happens is this: they still prefer the larger reward versus the smaller reward. But if they have to work harder for the preferred reward, then it shifts their behavior. So they decrease selection of the high effort activity, but increase selection of the low effort activity.
So lack of dopamine is just kind of like laziness, essentially.
Well, yeah. I mean, to me, right, laziness is closer, if you want an approximation, laziness, lassitude, anergia, lack of energy, those are closer approximations than anhedonia, lack of pleasure. And so one of the things that's interesting about this is this task has been translated to humans. So there's a researcher named Michael Treadway. He developed a human analog of these effort-related choice tasks. And he's shown things like if you give a non-pathological person amphetamine, the stimulant drug, which increases dopamine transmission, that it increases selection of the high-effort option, which is interesting because that's consistent with our view of what happens when you interfere with dopamine. He's also shown that, for example, people with major depression are more likely to select the low effort options. So in a sense, they're biased towards low exertion of effort. Now that in itself is an interesting finding because it taps into a whole literature on the symptoms of depression. So depression isn't only about self-reporting a negative mood or a dysphoric emotional state. It's also, for many people, it's about lack of motivation.
Yeah, sort of an unwillingness to do anything about it.
Exactly. And so having seen that literature emerge, what we've been doing most recently is to try to develop explicit models of some of these motivational symptoms by exploring manipulations that are thought to be associated with depression in humans. So, for example, one of the things that we've looked at is what are called pro-inflammatory cytokines. So what are cytokines? They are peptides that are released as a part of your immune response, largely a response to infectious disease, but they have various motivational effects. So, for example, some pro-inflammatory cytokines are given to people in some cases as treatments. People report not only depressive symptoms, but especially symptoms like anergia, lack of activity, fatigue, those kinds of things. And what it's sometimes compared to is something that I think most people have experienced. Have you ever noticed when you get an infectious disease, let's say when you first start to get a cold, one of the first things that happens is you feel fatigued. And you just sort of feel like, oh, if I just want to go home and lay on the couch and put a blanket over myself. So I think a lot of people have experienced this. One of the factors that contributes to that is pro-inflammatory cytokines. So here's an example of how you do essentially a sort of a preclinical study. You get a manipulation associated with depression. You see if it has the predicted effect, which is this effort-related effect in the model. But then you take it one step further and you try to reverse that effect by giving a drug that would improve performance. And so we've done that in the case of the pro-inflammatory cytokines. Another drug we've looked at is a drug called Tetra Benzene. So what does Tetra Benzene do? It basically depletes catecholamines, so dopamine and norepinephrine, but it has its greatest effect at low doses of depleting dopamine. And it does that because it blocks the storage. The storage mechanisms in nerve cells protect the neurotransmitter from being broken down by enzymes. So storage is a way of keeping stores of dopamine ready for release. Well, this drug blocks that storage process, so it leads to a depletion of dopamine. And why we picked it is because this drug is also associated with depressive symptoms, including what is called fatigue. The drug is given, for example, to Huntington's disease patients, but side effects like depression, motivational symptoms, fatigue, etc., are reported in the literature. So we published a paper a couple of years ago showing that Tetra Benzene induces effort-related effects. In other words, changes in those procedures that I was describing before, a decreased selection of high-effort options. And then the question is, can it be reversed? Can you have a drug that would actually improve the motivational performance in a Tetra Benzene-treated animal? We tried the adenosine A2A antagonist, MSX3, and that worked very well. It restored the normal performance across multiple tasks in Tetra Benzene-treated animals. And then we've also started looking at antidepressant drugs with various characteristics, and this has turned out to be interesting. The first drug we looked at is a drug called Bupropion, the trade name for which is Wellbutrin. So this drug basically increases transmission for dopamine and another neurotransmitter, norepinephrine. How does it do that? It blocks a protein that's called the transporter. So the transport protein, or the uptake protein it's sometimes called, is on the nerve terminals. And what it does is it removes the neurotransmitter from the synapse, from the synaptic cleft. So it's a way of inactivating the neurotransmitter. Well, if you give a drug that blocks that, it leaves more of the transmitter in the extracellular space. So it increases transmission of that particular transmitter. Now, why we picked that one is because it turns out not all antidepressants seem to work in humans equally well on these motivational symptoms, but that was the antidepressant that most of the literature said, well, if any drug works better, it's this drug. So we've tried that. And bupropion indeed reverses the effects of Tetra Benzene across 3 of the different tasks that we've actually tested it on. So again, you interfere with effort-related functions with Tetra Benzene, but you restore the normal pattern of behavior by giving bupropion. And we've published those papers too. And now we have some work that's not published yet. I don't mind talking about it though. So what about SSRIs, for example? As a group, the most commonly used antidepressant drugs. But when you dig into the human literature, you find something interesting. It's reported that although SSRIs, like Prozac, for example, or Lexapro, although they improve self-reported mood and they reduce anxiety and they reduce rumination, all important depressive symptoms, that they tend to be less effective at treating motivational dysfunction. And in fact, there are some depressed people who actually have worse motivational function, increases in the self-reported fatigue on SSRIs. So interestingly, when we tested Prozac, fluoxetine, in our model, we did not get an improvement in motivational performance. And in fact, if anything, at high doses, it actually made performance worse. So what this told us is something that links into an interesting trend in mental health research, which is to look at individual people and individual symptoms and the individual neural circuits that mediate each symptom, rather than lumping everybody together and saying, well, they're all depressed, and depression is kind of this unitary entity. Instead, looking at something like depression from the standpoint of, well, some people who are depressed gain weight, some people who are depressed lose weight. Some people who are depressed become more agitated or have more anxiety-like symptoms. Other people actually have profound psychomotor motor symptoms that even kind of resemble some of the symptoms of Parkinsonism. So not everybody who's depressed is exactly the same. Not every antidepressant drug works in the same way, nor do they treat each symptom equally. So different drugs seem to work better on the different symptoms. This way of looking at psychological disorders is now kind of put under this rubric of what's called the RDoC, the Research Domain Criterion Approach. And this was something that was offered by NIMH, the National Institute of Mental Health, a few years ago. There have been several publications on it, basically trying to promote the idea that researchers should not be locked in by traditional diagnostic categories and think only in that particular way, but rather think in terms of specific symptoms and the neural circuits that mediate those symptoms. But what I find is it enables me to understand our area of research better. Because, for example, if you ask me, well, based on your studies of dopamine, do you feel that you're modeling depression per se? And I think, no, we're not. What we're doing is we're modeling something that is a feature of depression, but it's also a feature of other disorders as well. We're studying basically a dopaminergic component of that. We're studying the related neural circuitry as well, but it's only a piece of the larger puzzle. And the way I think eventually treatment is going to go in the future is that we'll be able to have both better behavioral measures and hopefully neural imaging measures that will enable clinicians to be able to identify types of depressed people or types of people with other disorders who have a preponderance of a particular set of symptoms, and then maybe make recommendations about treatment based on the particular symptoms and the neural circuits involved, rather than just sort of blanket treatments based on general diagnostic categories.
When we think about motivational problems, depressed people are the first people that come to mind. What's the opposite end of the spectrum? Would that be like an extreme risk taker?
I know what you're saying. I think the classic answer would be people who are manic, who are in the manic phase of bipolar disorder. Unipolar manics would be the opposite end of that. And that's one of their characteristics. They do take a lot of risks. Dopamine systems are associated with risky decision making as well as effort-related decision making. So I think your point is very good. But in terms of traditional pathologies, I think the manic end of the spectrum tends to be the opposite of what we're describing as this anergic depression. And people who have bipolar disorder, they describe it that way. They report it that way.
Another thing I wanted to go back with on your rat studies, and I guess the human studies also, is when you were looking at motivation, it all seemed to be the carrot rather than the stick.
The literature showing that interfering with dopamine interferes with avoidance performance, so that's the stick end, as you call it, is actually older than the literature showing that it interferes with positively motivated or positively reinforced behavior. So in fact, it was shown many, many years ago when the first antipsychotic drugs were being developed that they impaired avoidance responding. And so they didn't know it when these early studies were being done, but it turns out they're dopamine antagonists. And the interesting finding that was reported, the classic finding in this area, is that if you give an animal a dopamine antagonist, you interfere with avoidance but not escape. And what does that mean? Let's say there's a light that turns on that signals that an aversive or stressful stimulus is going to happen. So avoidance is what happens after you learn that and experience it. When the light goes on, then you leave. But if the light goes on and you sit there and you wait, but then the aversive stimulus happens and then you move, that's called escape. And so the classic finding was dopamine antagonists interfered with avoidance, but not escape. So yeah, the dopamine works with both the carrot and the stick. And then the thing is that even what we just recently have shown is on the positive reinforcement side, it doesn't even have to be food reinforced. So the idea of the carrot kind of reminded me of this. So we just developed a procedure in which it's like that it's the T-maze task, but it's a different way of doing it. In one arm, they choose a running wheel. If you've ever had a rodent pet, you know that running wheels are something they will frequently do if given the opportunity. Mice do it, rats do it, gerbils do it, hamsters do it. So they have a choice between running in a running wheel in one arm versus going to the other arm and drinking a sucrose solution. So it's like being active or being a couch potato. That's and eating the Cheetos on the couch, right? That's the sucrose solution. And so, the way we develop the task, animals will choose more so to run in the running wheel. But if you give a dopamine antagonist or give that drug Tetra Benzene that depletes dopamine, it shifts their choice behavior. It decreases the selection of running in the running wheel, but actually increases selection of the sucrose and increases consumption of the sucrose. So essentially, the bias that's produced towards low effort activities is not just true of, let's say, lever pressing for food. It's also true for this activity that kind of in itself is intrinsically reinforcing, which is wheel running.
For people that they're not depressives, they're not manics, they're not necessarily looking for a pharmaceutical solution to management, are there food precursors that would increase the amount of dopamine that one has readily available in the brain, things like that just might be handy tricks for people to know?
I think the best thing is to eat a balanced diet from the standpoint of amino acid content. So the amino acids that are most vital are tyrosine for dopamine synthesis and also phenylalanine. So tyrosine is the immediate amino acid precursor of dopamine. So tyrosine is converted in the brain to L-DOPA, which we all know is a drug that's used to treat Parkinson's disease, but it's also a molecule that's made in your nervous system. Tyrosine is converted to L-DOPA, and then L-DOPA is converted into dopamine. Now, it turns out, though, if you didn't have much tyrosine in your diet, you could get it another way. You could eat foods that have a lot of phenylalanine in them, and phenylalanine can be converted into tyrosine. So this strikes me because a lot of people, they don't look after how much protein they have. If they eat a lot of junk food that doesn't happen to have a lot of protein, or even lots of people eat vegetarian diets. And for some people, a vegetarian diet means doing research and finding out and mixing beans and whole grains and getting the right amino acid content. For other people, a vegetarian diet may mean eating potato chips and a few other things, and they're all vegetables, so they're fine. You know, some people will balk when they hear that, but trust me, I know individual people who eat that way. And I think from the standpoint of synthesizing dopamine, it's vital that you don't eat that way. And if you're going to have a vegetarian diet, you want to do what a lot of vegetarians do. They know, well, gee, then I need to eat some of this, some of that, some of the other stuff to get that amino acid content to balance things out. And one of the interesting things I've started to realize too is if a depressed person doesn't eat normally, they could be making their situation worse because they're not giving themselves the amino acid content that promotes normal neurotransmission. And this is not just true of dopamine, this is true of other neurotransmitters. So serotonin, the amino acid precursor for that is tryptophan. So again, eating a diet that includes reasonable amounts of tryptophan, important in terms of maintaining serotonin synthesis. But now there's another thing that's interesting to keep in mind, because some people might think, well, if some tyrosine and phenylalanine is good, then more must be better. Maybe it will stimulate me. And the problem with that is, let's just say you are eating a balanced diet. You do have a variety of amino acids, and it includes tyrosine and phenylalanine. You're maintaining your normal dopamine synthesis. But in fact, under normal nutritional conditions, the enzymes that convert, for example, tyrosine to L-DOPA, they're relatively slow, so they are in a state that's called saturated. Meaning what? If you eat more, you're not going to synthesize dopamine any faster because you've saturated the enzyme. So sometimes, I think people who are wanting to do nutritional manipulations to manipulate some of these motivational conditions, the rule should be maintain normal levels, but don't overdo it. Overdoing it probably doesn't do you any good.
Smart Drug Smarts.
I thought that was just a really interesting explanation of dopamine. I feel like after that I have a much clearer understanding of what dopamine feels like and kind of can make assumptions about different states of mind when I might have more or less dopamine in active deployment within my brain. And it's interesting thinking about how that linear growth of motivation, I guess, that probably goes along with dopamine results in the famous inverted U curve of actual performance, that if you're so motivated that you're undiscriminating in what you're motivated towards, which I guess is sort of how you would characterize a manic state, that you become incredibly vigorous but kind of useless. And I guess that's sort of the neurochemical job that we have for ourselves if we're trying to be high performers, is keeping those dopamine levels at just the right optimal level of motivation where you're willing to do the hard work but still discriminating as what hard work is actually worth doing. I'm not sure which neurotransmitter is going to be next in the Know Your Neurotransmitters series, but it might be oxytocin, but it might not. If you've got a favorite neurotransmitter that we haven't done yet, definitely tweet at us or drop us an email, Jesse@SmartDrugSmarts or SmartDrugSmarts on Twitter. Or, of course, you can visit smartdrugsmarts.com on the web where we have a suggestion box page. And now, for those of you that hung around for the whole interview just to hear about sex with robots, Here's the ruthless listener retention gimmick.
Smart Drug Smarts. Ruthless listener retention gimmick.
First of all, I should point out that I mischaracterized this poll. This is an omnibus poll, and it wasn't strictly about sex with robots. It was about some robot servant stuff too, but 2 of the 4 questions were about sex with robots, and that's a bit more salacious. That's what caught my attention and probably what caught yours too. So in this poll, people were asked, if it were possible, would you like to have a robot as a servant? Would you have a robot care for an aging relative? Would you ever have sex with a robot? And would sex with a robot classify as cheating? Now, I'm clearly on the lunatic fringe. I mean, I do a podcast about smart drugs, but I was kind of surprised at how few people actually would have a robot as a servant. The total number of people polled was 1,000 folks, so not a small number, and only 33% wanted to have a robot servant. Kind of weird, right? I mean, why I would like to ask the other 67% why they didn't. Males were slightly more likely than females to want a robot servant. People between the ages of 30 and 44 were slightly more likely than people under the age of 29 to want a robot servant. Races seemed about equal on it. Whites, blacks, and Hispanics were all right around 33%. But moving right along to the sex, only 9% of people expressed interest in having sex with a robot. And surprisingly to no one, it was males that were more likely to be interested. 14% of males, only 4% of females. College grads were twice as likely as people with a less than high school education to want to have sex with robots, 5% versus 10%. Hispanics were twice as likely as white people to be interested in sex with a robot, 15% versus 7%. And Republicans were about twice as likely to want sex with robots versus Democrats, 11% versus 6%. So not giant numbers from any of these groups. Less than 50% of both genders would consider having sex with a robot as cheating. 46% of women and 38% of men. And although we already heard that Republicans were a little bit more willing to have sex with robots, they're also more likely to consider it cheating. 53% of Republicans considered robot sex cheating, whereas only 36% of Democrats felt the same way. I'm trying to think where I weigh in on this. I kind of feel like, yeah, if the robot were the right kind of robot, if the robot did it for me, then sure, I'd have sex with a robot. And I kind of do think I would consider it cheating also. It's like, if the robot has transcended being a kitchen appliance to the point where you'd want to have sex with it, and no, I wouldn't have sex with any kitchen appliance I can think of, then I think that, yeah, you would probably have to consider it cheating. But interesting question, fun to think about, and cool that this is like a plausible enough possibility in the not inconceivable future that people are actually doing big research polls on this kind of topic.
Smart Drug Smarts, the podcast so smart, we have smart in our title twice.
And that is the entire episode. Thank you for hanging around until the end. I hope you enjoyed it. And if you did, I will encourage you, as usual, to tell your brain-owning friends about Smart Drug Smarts, graffiti it on walls, stencil it on pieces of paper, write it in code and leave easy-to-find decoder instructions lying around, and all that good stuff. The show notes for this episode will be online at smartdrugsmarts.com, including the links to everything that we talked about. And I will be back at you next Friday, same time, same podcast, and with the same unflagging commitment to helping you fine-tune the performance of your own brain. I'm not exactly sure yet what next week's episode is going to be, but it's probably a toss-up between aniracetam, which has kind of become my go-to drug for creativity sessions, and an exploration of futurist ethics with somebody who does a lot of philosophical futurism. But you'll just have to come back and find out. That'll be episode number 75 next week. Until then, have a great week and stay smart.
You've been listening to the Smart Drug Smarts podcast. Visit us online at www.smartdrugsmarts.com and subscribe to our mailing list to keep your neurons buzzing with the latest in brain optimization. Smart Drug Smarts should be listened to for entertainment purposes only. Although some guests on the show are medical doctors, most are not. And the host is just some random guy. Nothing you hear on this podcast or read at smartdrugsmarts.com should be considered medical advice. Consult your doctor and use some damn common sense before doing anything you think might have a lasting impact on your brain.